All right. Welcome, everybody. One thing we can all get excited about today is that by the end of class, you'll understand all of that. Isn't that exciting? Math is not something to be afraid of. Math is something to be happy that other people are afraid of. Part of that. Go ahead.
Concentrate how we're involved in our capitalist society.
In a sense, yeah. In your hand. Here's how. In a capitalist society, you have the right to choose what job everyone wants. In a capitalist society, companies typically like to pay people for doing a job if they're good at the job. If they're not good at the job, in a capitalist society, they have the right to fire you. If you're very good at the job and multiple companies want you, they have the right to pay you more. STEM fields, computer science, anything that has reality under it, you know, medicine, rocket science, anything, like even stock markets, there is an underlying reality. Mathematics is the language of it. If you pursue a field that has math underneath it, and you're good at math, not scared of math, you will get paid more, you will get better jobs. Don't be afraid of math. Okay, I want some quick, simple answers to that question. What is a tree? Okay, good answer. That's true. What else? Not a bush. Okay.
Actually, it's we using coding to store certain kinds of data so that we have spreads. Other portions of data.
Very true. But actually, I was looking for the other trees. So the first answer, what other ways do you have to define a tree, like the green ones that you see outside? All right. You have just summed up for us the standard answer. You've got, you know, roots, you got a trunk, you got a canopy, you got a leaves, you got outer bark, inner bark, hardwood, sapwood, campion, whatever, the different parts of it. Reductionism. Does that word mean anything to you guys? The idea is if you can reduce something to its parts and understand what each part does, then you understand the whole. Is that true?
No.
Who said no? All right, why?
H2O doesn't behave like oxygen or hydrogen.
Very good. That's a great example. H2O doesn't behave like oxygen or hydrogen. It is its own thing. Another place that statement where reductionism fails is with complex system dynamics. So if you take a bunch of cells, you know, pluripotent stem cells, right? And have each one of them on their own. Watch how they act. They would just act like single cells. But put it together, the right kind of cells at the right time, the right place, they will grow up into a human being. So things together sometimes exhibit very different things than they do apart. But the thing we want to focus on here is this concept of dividing something up into its parts. There's many ways to do this. This is one way. It's the typical Western thought kind of way of dividing up a tree. Every kid learns this when you draw, but kids oftentimes don't even think about the roots. But think about all the other stuff that's going on with a tree. It's a surface for insects to live on. It's a node in a network, in a mycelial network, that's communicating with the roots of that tree. And there's nitrogen and phosphorus and potassium being shared in the root systems and the mycelial networks. There's levels in the jungle, and there's different ecologies at every level. It is a place where sunlight gets turned into oxygen, CO2. So a tree can be divided in many ways. You can divide it into trunk, branches, leaves, roots, etc. But it's also a meeting place of matter and energy. It is also a pattern, a DNA encoded pattern for protein deployment. That's all your DNA does. It tells ribosomes which proteins to make. So maybe it's just a pattern for that. It's also a collective cooperation between trillions of cells. So one way to divide up a tree would be into its cells. Or you could divide it up into the elements that make it. Here's a bunch of oxygen, carbon, and nitrogen. I'm trying to get you to realize there is no one right answer when you partition something into pieces. Keep that thought in your head. Now, questions about homework and things like that. This, if you remember, is the function that gets minimized. It's going to happen automatically for you if you use the scikit-learn package. That's fine. This is what's getting minimized. Now, why is it negative? Why is there a negative sign there? Why would your cost be negative?
If whatever you're taking inside the log is less than 1.
Exactly. So when y is actually positive, then this value is your probability. When y is 0 or false, this is your probability. In each case, a probability is a value between 0 and 1. So negative log of that is now a positive number. That's our cost function. When we did linear regression, we tried to minimize the average sum of the squares, right? Now your heads, you can remember, wasn't that long ago? Here, trying to minimize this. Now, for extra credit, there is a way to calculate this. It's not easy. Do it if you want. But if you want to show how accurate it is, just do the normal things. Get the accuracy, the confusion matrix. Make sense? Okay. At least one of you still didn't put their name at the top of the IPYNB file. Some of you didn't finish the time, and I will check back from time to time. Some of you put something there, but it really looked unfinished, so I just assumed it was unfinished, and I'll come back to it. If you still want to finish, please do. Some solvers would get stuck, or they would repeat steps. Some of you guys talked about this in notes. There is a reason why in A star, it should never repeat steps. Let's say we have a game state here, and we have a heuristic that gives us a number. Let's say it gives us a 100. No, that's gonna be G first. All right, yeah, G first. So you start off with 0, at heuristic give us 100. And then we do this step, and this step, this step, this step. Now let's pretend that this game state is identical to this one. So let's start next to it. Let's say that in terms of where the blocks are, this game state just happens to be identical to this one. The heuristic, therefore, will be identical. Right? But we took 1, 2 moves to get there. So, first of all, whenever you are going to expand all the children of a node, you only choose the one with the lowest G plus H. So it's possible that you will get here and 102 will be the lowest G plus H, but it's increasingly less likely. The deeper you get down, the higher G gets. The higher the G gets, the less likely it is that you're going to expand nodes that are equal to state you already did. And if you want, you can always just ignore it. You can have a separate hash function on this state that says whenever I come across something that's already expanded, I just ignore it. Any questions there? Okay, the fastest solver always took maybe a few milliseconds. It was amazing. And it was not admissible, which is fine. It was near admissible. What it did was it extra punished sometimes. You give like a punishment of 3 on something that would likely take, 1, maybe 2 extra moves, but it gave a little extra punishment, and that made it not admissible, but it still worked great. One of the reasons it worked well, because I believe it had a convex hull. If we simplified everything down to 2 dimensions, or no, I'm sorry, 1 dimension. If we just look at 1 dimension, some x, and this is the value of our heuristic. And let's pretend that we know that right here is the optimal answer with 1, 2, 3, 4, 5, 6, 7, 8, 9. A convex hull, every time you change position, if the heuristic gets better, you get closer to the answer. That's what you want. You want to be closer to the answer every time your heuristic gets lower. Same thinking for gradient descent. With heuristic, you're not calculating gradient, you're just taking chances or recomputing. And there are cases in machine learning where that happens too. When do you think that might happen? When do you think you might have to pull this strategy out of the box and try it again? When would you not be able to compute gradient? Have any of you taken calculus? Yes. Are there non-differentiable functions out there? Yes. That would be a scenario. Another scenario is if the space which you're exploring are points in a possibility space for a complex system. Complex systems are very unpredictable and non-linear. Okay. Just to make sure there's no confusion on the confusion matrix. the standard way to do it is to do predictions on the columns and the actuals on the row. So if you predict yes or no, or 1, 2, 3, or no yes, I don't mind if you flip those two, but predictions on the columns, actuals on the rows. All right. One of you asked a very good question before class. When using the logistic regression package, do you need to submit something for the arguments? The one that I want you to pay attention to is C. Who remembers what that is? You know, you guys are allowed to look back at the slides after class. It's not a sin. Okay. It's the one I highlight right there, bright green. It is the regularization parameter. And it's going to come up again in today's class. Who remembers what it's for? Yes. Yes. It not directly, but indirectly. So what it does is it adds, it's like, you know, this little extra in here is the regularization parameter, specifically this. So that C is represented by lambda here, but actually 1 over lambda or whatever. But the point is, if you make these W's too big, you get punished. So it makes you want to make the W's small. And those W's are the same as those betas. The effect of it is to smooth it out. So without regularization, if you try to minimize that cost function as much as you can, you'll get this. You get almost a square function. That's not realistic. It's not generalizable. So you add the regularization parameter and you get this. It becomes smoother. Now, in this one-dimensional scenario, that doesn't change a whole lot in terms of the outputs. But when you get more complicated, it will. Now, we only had beta 0 and beta 1, but when you get beta 2, beta 3, and a more complicated function, it's on 2 dimensions, you might get something like this, where think of that as a mounting contour. Everything that's true is above a certain threshold. You're looking down on it from above. That is perfectly accurate, not generalizable. The idea is to use the regularization parameter to force it to be smoother, and it comes out like the purple line. Now we're doing this in a very simple one-dimensional scenario or 3-dimensional, so that you get the idea, and these ideas will be helpful when you go into higher dimensions later. So if C is 1 by default, please experiment. Experiment with 2, 3, 0.5, 0.3.
Do you care how many like dimensions we have for our x's, like how many like x1, x2 do we have?
I don't care. Make sure they all make sense. And maybe a good amount of like x1, x2, x3, and I want you to show them. Use something like matplotlib, and obviously it's hard to see in 4 dimensions. So you can do them each one at a time. X1 versus y, x2 versus y, x3 versus y. That's the simplest way to handle it. And On each of those, put the points and the curve. So plot the points and the curve. That would be, you take your X and Y's, and the Y's are all 1 or 0, right? And the X's were there, so you'll have a bunch of these and a bunch of these, and you'll have some curve. Maybe this is, for X1. You do something similar for X2 and then X3. You can have 10 X's if you want, or 1 X. All right, any more questions? We got more fun stuff coming. Okay, I mentioned partitioning. These are all terms that do kind of the same thing. Partitioning or quantization. Discretization comes from the word discrete, not in terms of keeping a secret, but in terms of being digital versus analog. And clustering. So maybe you're taking things that are all together or in a continuous space, and you're putting them to boxes or categories or areas. The simplest example is just one dimension. Let's pretend we're analyzing something based on its mass. And maybe it's planets versus asteroids. Or planetoids, whatever. The things of a certain mass, we call them one category. And the things of a lower mass, we call them another category. What do you think is going on in between? What kind of math might be involved there? Think simply, complex. No, not gravity. Nothing so complex. You're just trying to find a middle point in between all the examples. And you want, if you have a really good classifier and you have an easy to classify system, then this and this should be as wide as possible. Same thing works for multiple dimensions. As we go up in higher and higher dimensions, what do you think we call this line? We said the word earlier on in the course. Hyperplane, yes. So oftentimes we'll draw something like this, and just like for the homework, I asked you to do, X1 versus Y, X2 versus Y, X3 versus Y. This could be one plot from 1,000. Maybe it's 1,000 dimensional, or a 999 dimensional hyperplane cutting between 1,000 dimensions of space. Make sense? So how do we find that line? Well, we want the quote unquote best split of the data. But there's a big assumption that we start with. The assumption is that the data is separable with the hyperplane. So we're assuming that from the get-go. And if that's not true, we find out and we have to use a different model. Or we have to use something called a kernel, which maybe we'll do later next time. But we have simple data today. It can be split by hyperplane. So that's what we do. And we want to find the very best split. Do we have to incorporate all of the points? No?
I mean, I guess you could get the same line just by getting the poles of the data as they generally be the middle ones.
The poles, like, where
Even
the
the ones
poles
that are like the anomalies, like the ones closest to the line and the ones furthest away. I mean, I guess you just need the closest one.
That's right, just the closest ones. Now remember, every one of these is a point in space, and oftentimes we talk about them as vectors, where the origin is the starting point of the vector, and it goes right to that point. So you can call this a vector, and this a vector, and this a vector. That's why we call it a support vector machine. See that title top left? The distance between the support vectors, this and this and this, and the line are as far as possible. So we don't need to look at all the points. We need to look at some of the points. We need to find those support vectors. And this kind of classifier works very fast. Next time, we're going to get into the math of that. Today, we're going to do some math, but not even that yet.
Well, wouldn't you not know which one would be closest if you chosen the points? So wouldn't you include the keywords or vectors or?
You have to go through some of them, yeah, but you may not have to look at all. There could be some ways to speed it up. We'll go through the math next time, and maybe you need to look at all of them at least once just to know where it is. But the important part is once you start to get close, it's just certain ones in the band that are going to make the difference. And you can even specify things a certain way, but typically we specify it like this. Who sees something familiar here? Well, it's y equals mx plus b. It's coming up again. Gonna come up all through this course. This, it says 2w, whatever, p for w. The width of this is the thing we want to maximize. There's pressure to maximize that. But we don't want to misclassify these. So we have this no man's land in between. No one knows where the line is because there's no points in there. But something tells me this might be a situation where we can have something very accurate that's not generalizable. What do we do in that situation? What do we need?
More data.
That helps, yes. A guy named Robert Mercer, who I don't agree with a lot of what he does, but he's a forefather in NLP. He said there's no data like more data. What else can we do if we want to make this not be so specific? We want to make it more generalized.
Can you like relax your maximization of the distance?
How? If we just have some cost function, it's going to maximize that forever. How do we make it not maximize it too much? What? It's not the best way to do it. The best way to do it is what we talked about maybe 7 minutes ago.
Do a C.
Yes, the regularization parameter. And scikit-learn still calls it a C, which is really nice. Anyway, this is how you use an SVM. So easy, isn't it? Good thing you don't have to program it from scratch. You just import it, take your X, get your Y, you create your SVCs, get your support vector classifier, you fit it, and then you make predictions. You're off to the races. Now, that C value, here we have a C of 2, that's 2 exponent -5, so 2 to the -5. and then 2 to the 5th. Those are very, very different values. So feel free to try a broad range of values for your C. When you have a very low C, that's a soft margin. It doesn't care that much that this is on the wrong side. But when you make C very high, it cares a lot. And here it's like, oh, I'm going to make sure I'm perfectly accurate. Even though this line is not very generalizable. As a human, which line would you choose? One? On the left? Me too. I want my machine learning models to apply to many situations I haven't seen yet. I'd rather have them be more generalizable and less perfect. There are scenarios where that may not be true. You want your autonomous driving to be perfect. Look at all that nice code up there. You guys can use this when eventually you do a homework on this. You have to remember it's there. Okay, now an SVM, support vector machine, is one way to partition a space. You're dividing it. That's almost the same as clustering. Clustering is you're taking this group and this group, right? And making them an object of some sort. They're now a cluster, it's not just a bunch of points. So instead of dividing everything into 2, clustering can divide into however many points you want, or how many clusters. You can divide into 1,000,000 clusters or into 10 clusters. One way to do it is to decide ahead of time how many clusters you're going to have. Maybe you use the centroid of each cluster. But density-based would be another way. And maybe you don't know how many clusters there should be, so you let density decide. Well, that's one way to divide the types of clustering or partitioning. Another way to divide them, same thing, just looking at it a different way. There's flat kinds and hierarchical kinds. Flat kinds be you have a bunch of points and you cluster them. Now you're done. What do you guys think hierarchical clustering would be?
Maybe some of the data points are like weighted, they have more value than others.
That's a very good idea. That's not what I'm going for, but just as a side point, in logistic regression, in your homework, there is a way to make some points more valuable than others. You can wait, but you don't have to. Hierarchical is more like a hierarchy. So let's say you have a bunch of points and you cluster them. And one of the clusters is extra big. So you know what? I'm going to cluster within that cluster. And that cluster has children. And then each of them maybe has children clusters, smaller clusters. So you can be flat or we can be hierarchical. Or we can be centroid based or density based. In fact, there's a lot of ways to look at this. And one way people describe these is parametric versus non-parametric. Parametric. So who here has heard of k-means clustering? All right. What is the k? Yep. What does it represent in that scenario? What's going to happen if you choose a k of 7? You're going to get 7 clusters. If you assume there are 7 clusters, you will get 7 clusters, whether they're good or bad. It doesn't know that. The computer doesn't know. It's going to give you 7 clusters. That is parametric. you're setting a parameter. But if you say, just cluster based on who's closest to what, or density, it's non-parametric. Now, the other axis here, we got flat, which means we got, we're just going to do it once. Now we have all our clusters. And then hierarchical is, can we go down further and further? And in the question marks, it's actually the best, and we're going to look at that in a little bit. Who here has seen something like this or know what these are? Voronoi diagram. So each of these black points was chosen. The regions were decided based on those black points. What do you think they were trying to minimize? What cost function might they have been trying to minimize to get these lines? Come on, some guesses.
Number of angles.
Oh, good guess. I never thought of that. Not quite, but that's a really good one. Minimize the different colors. Have you ever heard of the 4-color map theorem? That's a fun one. That's not it though.
Is it like the amount of sides each one can have without touching one of the same color?
No, but we're getting closer. That's similar to the angles one. We're getting closer. Minimize something.
Those lines are the like midpoint of distance between the two dots and their perpendicular.
Yes. We're talking about distance. So if you're in this, whatever you call this, dark orange area, every point in dark orange area is in a sense closest to this dot over all the other dots. What distance function do you think they're using?
Euclidean.
Okay, might be Euclidean. That would be the L2 norm. Who here thinks it's a different norm, like the L1 norm or the L3 norm? Okay, I'll raise your hand for the L1 norm. Raise your hand for the L2 norm. Raise your hand for the L3 norm. Who didn't raise their hand? Okay. Let's find out. Did those Voronoi regions make you think of soap bubbles at all? They made me think of soap bubbles. That's why I brought this up. Soap bubbles, of course, there is no black point we're trying to measure a distance to, but they end up making very similar partitions of a 3D space, 3D volume. They're not trying to minimize this, they're trying to minimize something else. What is it? No, surface area. There it is. They're trying to minimize surface area for a consistent volume. They do it faster than a computer. It's actually a computationally rather difficult problem. Do it faster than computers, at least last I checked. Computers get faster every day. Trying to minimize surface area, somehow they come up with similar shapes as when you're trying to minimize distance to a point inside the region. One thing you'll find in mathematics again and again is that there's many ways to look at the very same problem, many ways to get there. This is the mathematics of soap bubbles. They can come in many different forms. Okay. We have here a bunch of blue dots. That's our data. We are going to find the L1 and the L2 norm, but which is which? The yellow dot is one of those. Is the yellow dot the L1 or the L2? Blue dot, which one? One's the one and one's the other. Okay, who thinks that the L1 norm is blue? Raise your hand. Who thinks that the L1 norm is yellow? All right, so all you guys think the other way, you just didn't raise your hands because it's a either or. This is which one, L1 or L2? No, it's L2. Now, we haven't exactly had this kind of nomenclature before. Whenever in math, if you see, something, some variable representing some anything, and you see this on the other side, typically that refers to the size or the distance or cardinality or bigness or something along with that. And if it's an L1 norm, they might put a 1 there. L2, put a 2 there. If it's L3, they'll put a 3 there. That's one way to write this. I know mathematicians come up with many ways to write the same thing, and it can get a bit frustrating. It's the L2 norm. And it turns out that yellow dot represents the L2 norm. And if you look back at here, it kind of resembles that. Now here, the black dots weren't allowed to move, only the walls between them. Those walls, the dividers, or the space was partitioned to minimize the L2 norm for every point. Okay, that's the L2. Now, this brings out the L2 norms. Maybe it's the L1 norm. What exactly is this then? It doesn't look like it's even repeating a norm, does it? It's a bunch of things equal to 0. It's a sum that equals 0. It's the center of mass. You can think about it as the L1. So for every one of your points in your data, you subtract a vector to the center of mass. So blue is the center of mass. For every one of these points, this minus this, plus this minus this, plus this minus this, plus this minus this. All those vectors add up to nothing. That means this is the average. See? Just averages out. Is there anything in this equation you guys don't understand? All right. Now, we're going to do K-means clustering. It's just a few steps. That's all it is. It is the simplest of the clusterings. So let's say we have a bunch of points. And we'll be really simple. we'll choose k equals 2, okay? We're gonna choose a k. Choose 2, the number 2, be very simple. Then we're gonna select k random points. So randomly, let's say we select this one and this one. Now, we can see as humans that maybe this is a cluster, maybe this is a cluster, so these are probably 2 poorly chosen points, but that's okay. This algorithm will fix that as time goes on. Okay. Now we need to assign each point to the nearest k. So let's say this is k equals 1, this is k 2. So obviously, this point goes here, 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 and we start to create a natural dividing line. And what we get is a Voronoi diagram. It exactly matches the Voronoi diagram, because we're using that Euclidean distance here. The Voronoi diagram, it divides partitions of space such that for every point, it is with or in the same partition with the centroid point or chosen centroid that is closest to. So we do this. Then, and let's understand this equation. Let's break apart the mystery. Who knows what this means? For all? For all. For all. Like the Three Musketeers. One for all. For all J. J is just a number. Now we know what K is, right? Because we said it. We said K to be 3 or 5, or in this case 2, or 1,000. We said K. So J is just every number between 1 and K. These are all natural numbers. Okay, J could be equal to 1 or equal to K, or it could be a 2 or 3 or a 4. Okay, so we know that part of it. So M is a central, or one of these things. We'll call them centroids, even though they don't really start off in the center. This is M1, this is M2. Who knows what the X's are? What are the X's?
All the other.
Yes. Now, in math, there's abuse of notation all over the place. So sometimes when I say X1 or X2, I'm talking about the dimensions of the space. Not here. Here, X1 and X2 will be, you know, maybe this is X1, and this is X2, and this is X3, and this is X4. So we could have X1,000. Okay. What is this distance here? Is that L1 or L2? L2. Now the number 2 that moved up here, this is from a different website, different book, whatever. Just gonna roll with it. You're gonna be learning from different books and websites your whole career. This right here is XB minus M. This is some point in the centroid. That's also the L2 norm. So we have here the distances, or the distance for some XB, for some point. Let's just choose some XB. Maybe this is XB right here. For that point, the distance to the centroid, L2 distance, is less than or equal to what the distance to the centroid? Somehow that doesn't make sense, right? What's the difference between this and this? What? Yes.
for each student.
Yes. So there's a piece that we're assuming here that's not actually in there. That I and j cannot be equal. This is for an I not equal to j. So let's say I is 1, okay? Then what we're saying is that for some xp, some given xp, we'll choose this one for now, xp, the L2 distance to mi, just do this one, is less than or equal to the same the distance from that same xp over to m2. This would be your mj. So this partitioning is such that for they're all xp such that, those two dots mean such that, for any xp minus m, or the distance to any m centroid I is less than or equal to the distance to all the other centroids. That's all it's saying. And no matter which point you choose, the distance to its own centroid is going to be less than the distance to all the other centroids. Now, this math makes sense, doesn't it? Is there any part of this equation that doesn't make sense yet? Please raise your hands.
Where's MI? Like, does that change or is it always?
It has to apply to all of them. So if you choose this as your MI, then the XPs for which this is true are these. If you choose this as your MI, then this becomes MJ, and you're talking about these.
So you'll do this calculation for every point at every section.
And when you do it in reality, you don't have to do all those calculations. Yes, you do actually, you do have to do it. So yes, you will do that, but you kind of get to do it once. This mathematical relationship puts into firm and very definable terms the relationship between any two points and their centroids, and that's what defines the partition. Okay. Then step 4 is the last step. We're going to recompute centroids. How do we do that? So this is one centroid, and here's another. If we wanted to recompute our two centroids, what would we do? Yes, we're going to compute another 2 points. And actually, they don't even have to be points that were represented. They could be in there somewhere. And you know what? One way to do this is to take the center of mass. So you take the center of mass here, and take the center of mass here. And those became your 2 new centroids. Or you could take the point that would minimize the L2 norm if you want. But the point is, make a new centroid. Then you go back to step 3, do that again. Is this one closer to this one? Yeah. That's closer. That's closer here. That's closer here. That's closer here. So this is no longer a centroid. It's no longer a centroid. But maybe they started off as original data points. We have now these 2 new points, and this line may shift. Our new dividing line could be here. Then we do it again and again and again. this recomputing of the centroids, you're just adding up the vectors, right? And then dividing by the number of things in it. It's an average. Also known as the center of mass. Okay, now let's try with the k equals 3. We have a bunch of points. We choose 3 random centroids. And we divide the space into those Voronoi regions. And then everything near the green point, we just call it green. Everything near the red point, we call it red. Everything near the blue point, we call it blue. Then we recompute our centroids based on an average of those points. And of course, that red one is brought down, right? Because these are just random starting points. This is now the only data point in the red region. So of course, the average of all red data points is going to be exactly that point. The average of all blue will be moved up a little bit. Average of all green will be moved down a little bit. And that's exactly what we see. That makes sense, right? Everybody following along? And then we do this again. How do you know when to stop? When they stop changing, right? When it's similar from one step to the next. Is that what you're saying? Yep. When the changes stop occurring, or when the changes are so small that it's not meaningful, and you can decide what that is. All right, any more questions on k-means before we move on to the next one? All right, this is DV scan. I don't know why it's called that. This is one of the things that is density based. So it's non-parametric. So you don't have to know how many clusters they're going to have. But what you do decide is how big are these circles. You could call this, a radius of epsilon. The blue, the yellow, the red points, those are all just data points here. They're just in your data somewhere. What do you guys think is going on? Just from this diagram, what do you guess? A lot of information in the diagram.
It's basically distance from each dot. It's B and C. And the circles of A is in.
Now, there's another detail. That's really good. But there is another detail. So this is the circle around B. How many dots total are in that circle? 2. This is the circle around this one. How many dots total are in that? 4. How many dots total are in this circle? 5. How many dots total are in this circle? So what's unique about the red circles? Why are they red? Say it again. At least a certain number of nodes. It's 4 in this case, but it could be anything. And the size of the circle could be anything. So we call it non-parametric, but really it does have parameters, right? Those two, at least, the radius of the circle, or in higher dimensions, it'll be a hypersphere. So the red ones, we call those the core nodes. They're nearer to many other nodes. Maybe those are likely to be a cluster, right? The yellow ones are reachable. They're near enough to be quote unquote reachable. And then the outlier nodes, they're not within anybody's circle, so they're just outliers. What's nice about that is real data has outliers, doesn't it? How did k-means handle outliers? Yes, it always includes every point in something, no matter what, even if it's totally an outlier and should not be included, it's very inclusive. Inclusivity is a good thing among humans, but we don't always need it in our data. DB-scan is nice because it can handle outliers. Another thing that's nice is it can handle any distance function. If you're in a weird space that's hyperbolic, now that's a very fun rabbit hole to go down to. What exactly is a hyperbolic space? What's the Minkowski space? There's all kinds of weird spaces out there, weird geometry. There are geometries where parallel lines do meet. Yes, that's a good rabbit hole to go down. But we can do any distance function. We can do clustering. And if it's noise, that's just outliers. As a human, how many clusters would you create here? And are we all in agreement as to where they'd be? Now, it's important to study clustering algorithms in scenarios that we can also visualize. Because once you get above a few dimensions and visualize it, we just have to trust it blindly. So let's see how the different methods do. Here we got some challenges. We've got different densities. So density is not a constant. We've got indefinite noise, things that should not be in any cluster. We got arbitrary shapes. And we got like a banana, kind of a Nike swoosh. We got different sizes. K-means gives us this. What are the problems with this cluster?
There's randomness, but sometimes there's something very close to just not the same cluster.
Yeah. Like it's hard to tell a little bit, but these are different colors. So these are different clusters. Even though as a human, obviously they're in the same cluster. Here too. And what's the problem with this point right here? It's an outlier. It should not be in a cluster with these. I mean, it makes no sense to divide up, partition the space this way. It makes no sense. K-means is good in some situations, but in higher dimensions, you might be doing stuff like this. Agglomerative clustering is another way. This shows what the agglomerative cluster is doing. What do you think it represents? What is it doing? Think about the word agglomerative. It's fun to say, isn't it? Agglomerative. It's glomming on. Glomming on is exactly how it works. Let's pretend you have, wait up, you got a couple of points. It's going to connect these two together into a tiny cluster of two. How does it choose these 2 points? It's going to choose 2 points that are far apart from each other or close. Maybe choose the closest. So it's going to take the 2 closest points and just agglomerate them together. Then the 2 second closest points and agglomerate them together. And the 3rd closest, and then the 4th closest. And eventually you're agglomerating something to a point in another cluster. So those becomes agglomerated. And you go up the chain, so everything's part of one cluster. All the data points. So obviously you don't want to cluster everything into one cluster. So you have to select somewhere to break, right? And there's many ways to do that, but when you do with agglomerative clustering, typically you come up with something like this. It's still not great, is it? Obviously, it's going to make, you can't have noise, everything gets agglomerated eventually. And this should not break right there. So agglomerative clustering, even though it works sometimes, it didn't work here. DB scan. I'll tell you what's good is that the noise is noise. That's nice. And this, that's a little better, right? A lot of this should be one cluster, but it didn't do so well here. It didn't do well here or here. Here did okay, but not there and there. Then what's this? Why is this and this in the same cluster? Makes no sense. So remember how I said you can set epsilon, the size of the circle that you consider these are the nearby points. This is for an epsilon of 0.01. If you make the epsilon higher, what do you think it's going to look like? Make those circles bigger. The things that are nearby are now more. What's going to happen to these clusters?
You like a lot less of them.
You get this. This is double the epsilon 0.02. And you get a fewer cluster. You know, this is much better. I like that. I like this. I think that it's saying these are the same cluster, and I don't like that. This is green. Why is that green? You know, maybe it's a little better, but it's not getting perfect. Not getting what I really want. This is epsilon 0.03. And now it's just no good anymore. So we need something else. HDB scan to the rescue. Hierarchical DB scan. Hierarchical DB scan gives us what you as a human thought it should. Remember, DB scan is the thing with the circles. And let's say we do that at one level, at the course big level, and then we go down inside each region, do it again at a smaller level, do it again at a smaller level. Maybe we start off at smaller levels and then bring it up. What you end up with is something like contour maps. Think of these as hills, okay? You have contour maps all over the space. This is probably a cluster, but if you were to go down the contour map to a low enough altitude, all of this becomes one cluster, which is not that great. So you want to be able to select the right altitude. And it turns out you don't have to select the same altitude everywhere. You can select different altitudes in different places. Think about these points again, like a 3D contour map. The height represents what? Who can tell me what the height represents there? The height of the mountain. Yes. Vertical density. And depending on which height you choose, you'll get in this drawing, of course, 2 or 3 clusters. Another way they look at it is that this goes on inside is you have a graph. Remember how some points were reachable versus not reachable? Outlier versus not? Well, if you make those circles big enough or do it at different scales, eventually everything's reachable, but how reachable is it? This is some of the math going on behind the scenes. And this is another way to look at the exact same thing. So this and this are at the same altitude, but this one's at a different. but you can choose the altitude for each cluster. And it's really nice that eventually you get this. So just remember that HDV scan is better than the others. Maybe that, if that's the only thing you take for you, yes, that's a good thing to take away. Any last question? Thank you, everybody.